Okay. Hello everyone, welcome to this 14th lecture in the NPTEL course on Riemannian geometry. So last time we introduced this notion of a connection on a manifold. So a connection is basically just a map which takes in two vector fields and spits out another vector field. So xy goes to nabla y with respect to x. Right, so you should think of this as the directional or covariant derivative of y with respect to this vector field x. It of course has to satisfy three properties, that it's R linear in y, so it's R linear in y. Then it's C infinity m linear in x, and in y it's not C infinity linear, but it satisfies a Leibniz rule, right? So sort of product rule. Two consequences of this are these locality properties, namely suppose y is identically 0 on an open neighborhood, then that implies that whatever directional derivative you take with respect to whatever vector field, that will still be identically 0 on that open set. Okay. But then because it's C infinity linear in the x variable, this imposes a much stronger locality with respect to x, namely if the value of x at a single point is 0, then the value of the directional derivative of any vector field at that point is 0 with respect to xp. Okay. All right. So the second property, what it implies is that one can safely talk about the directional derivative of y with respect to a single vector xp, right, because of this second property. So today I want to refine the first property, but before we can do that, in this lecture I want to refine the first property, but before we can do that we need to understand how to write down our connection in local coordinates. Okay, so the first thing I want to do is understand the following consequence of locality. So let U be an open subset of M, and let us say nabla is a connection on M. Okay, then because of the locality, nabla induces a unique connection on this open set U, which I continue to denote by this symbol nabla. So this takes in a vector field which now is a vector field only on this open set U, times a vector field which lives only on U, and spits out another vector field which lives on U, such that for all vector fields on the entire manifold, if you restrict those vector fields on U, then this connection nabla, which may be I'll denote by nabla U, is simply you take the original connection, apply it to y and x, y tilde and x tilde, and restrict that result to U. Okay. So in other words, if you have a connection on M, you can now restrict it to a connection on this open set U. And the point is that this sort of restriction is well defined because of this locality property, the first locality property. Okay, so what is the proof So the proof is for any xy in which is a vector field on U, let x tilde y tilde be any extensions to vector fields on all of M. Okay, so you extend x and y arbitrarily to vector fields x tilde and y tilde, and define this nabla u of y with respect to x. You just define it to be this. Okay, and then locality 1, the first property implies that this is well defined and independent of the extensions. And then one can easily check that this satisfies the axioms of being a connection. Okay. So as I was saying, this just means that given any connection on M, you can now restrict the connection on an open set of M. So that helps us write down what our connection will look like in local coordinates. So the next thing I want to talk about are the so-called Christoffel symbols. Okay, so let nabla be a connection on M, and let's say U is an open set such that there exists a local frame E1 to En for the tangent space on U. So then this quantity makes sense because you can, as I said, you can restrict your connection to the open set U, and each of these are basically vector fields on this open set U, right? So so one can applying the connection to those makes sense, and moreover, because this is a frame, this new vector field will be a linear combination of those vector fields, right? So so then there exists these coefficients gamma I, j, k, which are sort of smooth functions on U, such that this is simply gamma I, j, k times E k. Okay, so these symbols here are called Christoffel symbols. So these are called Christoffel symbols. All right. So so more generally, if X is a vector field on M, Y is a vector field on M, then the restriction of X to U can be written as Xi Ei, again using Einstein's summation convention. The restriction of Y to U can be written as Yi Ej, Yj Ej. So then you can try to compute what this is. Well, this is just going to be this Ei times Yj Ej, but now we use the properties of being a connection, namely it's C infinity linear in this and it satisfies a Leibniz rule in the y variable. So if you simplify, this is going to be Xi nabla Ei of Yj Ej which is going to be EI applied to Yj times Ej plus Yj times nabla EI Ej. Okay, so that's going to be Xi times EI applied to Yj times Ej plus Yj gamma Ij k times Ek. Okay, so now if I want to pull out an Ek common, I just change this variable and this variable to a k, right? I mean, they're just variables in a summation, so I can always use whatever letter I want for those variables. So this will now be Xi times EI Yk plus gamma Ij k times Yj whole times Ek. Okay, so we have the following local formula for the connection on this open set U in terms of a local frame and these Christoffel symbols. Okay. So this quantity here, I have a special name for it. So so I'll introduce some notation. So whenever I write something like this, by definition, this basically means that I am looking at the kth component of the derivative of y in the eith direction. Okay, so that's going to be my my notation. And similarly, if I for any other vector field, this is basically by definition going to be the kth component of this. Okay. So one thing to note is, unlike in regular derivatives on Rn, this also depends on all the other components right via this this sort of zeroth order correction term, right. So this is how a general covariant derivative differs from the naive derivative in Rn, in that the derivative of the kth component also depends on the other components, right, through the zeroth order correction term. Okay, so that's something to be sort of careful of. Okay, so so if I apply the above formula, so let me maybe write it down again. So if you apply the above formula to x equals di, where di is with respect to some coordinate system, then this is just going to be the and if you look at the kth component of the derivative of y in the ith direction, then this is simply going to be this. Okay, and so then the full covariant derivative is basically just going to be this. Okay. Alright, so now I can actually use this to as I was saying, to prove a refined locality. So this is the following is a proposition. So this is what I'll call locality part 2 or refined locality. So let xy be vector fields and P be a point in M, and suppose gamma is some curve such that gamma of 0 is P, so it passes through this point P, and the derivative at 0 is precisely xp. Okay. So now suppose y of gamma of t is 0 for all t, right? Then my claim is that if you compute the derivative of y with respect to x and evaluate it at p, you will be 0, right? So remember what the original locality was, that if y is 0 in a neighborhood of this point p, then no matter what x is, you take the derivative with respect to x, that will be 0. Now what this says is, you suppose this is your m, this is your point p, and this is your vector x, xp. Then as you take any curve and suppose y is identically 0 along that curve, then that basically implies that the directional derivative of y with respect to x is going to be 0. Okay. So in most applications, we take gamma to be an integral curve of x. Passing through p. Okay. All right. So let's prove this. Okay, so let x1 up to xn be coordinates near p, and let's say del 1 up to del n the standard frame for Tm with respect to these coordinates, right? And suppose my vector fields are given by x equals xi del I and y equals yj del j, right? So then what is our sort of formula for this? That is precisely xi del yk by del xi plus gamma ijk xi yj del k, right? So let me call this star. But now if you evaluate yk along this curve gamma of t, that's obviously 0 because y restricted to gamma of t is 0. So in particular all components are going to be 0. So in particular when you take the derivative, that's going to be 0, but by chain rule the derivative of this is precisely del yk by del xi times the derivative of the ith component of the velocity vector. So now when you plug in t equals 0, this implies that del yk by del xi at p times xi at 0 is times this velocity vector. But what is this velocity vector at 0? Note that gamma dot at 0 is simply xp. Okay. So this is simply going to be xi p, that's 0. Okay, so also yk at p is 0, yj at p is 0 for all j. Okay, so now if you plug this into this formula star, at p you see that the first term is 0 because of this, and then the second term is also 0 because this is 0. So you get that the derivative of y with respect to x at p is 0. Okay. Alright, so what is the upshot? So the upshot is that we get a formula for computing we get another formula for computing the connection. So if gamma is a curve and x and y are vector fields such that let's say gamma is an integral curve of x, so that just means that x evaluated at gamma t is precisely the velocity vector of gamma, and then we put y of t to be the restriction of y to gamma of t, then we have the following formula. So if you compute the derivative of y in the direction of x at any point on this curve, that will equal the following: d by dt of yk plus gamma ijk on gamma of t times the ith component of the velocity vector of gamma times yj of t times dk. Okay, so if we take an integral curve of gamma, then we just restrict our y to this integral curve, and then using ordinary sort of time derivative along that curve, we have a formula for the connection at any point. So you have this curve at any point here, your xp is in the direction of the velocity vector. In fact, it is the velocity vector of this curve. So at this point you can compute this quantity by simply using this formula. Alright, so maybe let me end today's lecture by giving you an example of a very sort of general construction of connections. So let M be a submanifold of Rn. So let me draw a picture. Actually, since this is going to take up some space, let me just do it on the next page. Right, so an example. So let's say I have this surface embedded inside some Rn, and suppose P is some projection from Right, so then the tangent space of M can be considered as a subspace of the tangent space of Rn. Now suppose P is a projection. Okay, what does a projection mean? That just means it's a linear map such that P squared is equal to P. Okay. So then using this projection, I can actually define a connection on M in the following way. Okay, so let x and y be vector fields and let P be a point on M. Let y tilde be any extension of y to a vector field on all of Rn. Okay, so one can always do this using partitions of unity, or one can even do this in a neighborhood of right. So let's say on all of Rn. Okay, so the picture is the following. So we have a P here, you have some vector xp that's tangent to your manifold M. So now y tilde is, you have another sort of vector field y which is tangential to your manifold, but then you extend it arbitrarily to a vector field on Rn. Then we simply define this connection applied to y in the direction of x. You simply take the Euclidean connection. So this is the trivial or naive connection on Rn, and you differentiate y tilde in the direction of with respect to xp. Now the issue is that if y tilde, because it's a vector field on Rn, if you differentiate it with respect to xp, even though xp is tangential to M, this result may not be tangential to M. So what you do is you apply the projection map. So you get some by taking the derivative of y tilde with respect to xp, you get some vector field, you get some vector in Rn, you just project it down to Tm, and one can check, it's a very good exercise. Check that this gives a connection, so it satisfies all the axioms. Okay, and note that this is actually independent of the extension. So the definition of this is independent of the extension, precisely because of this refined locality theorem. Why? Because recall that this depends only on the values of y tilde along an integral curve of x, right? But because x is tangential to xp is tangential to M, you can always pick an integral curve that remains tangential to the surface, right? So you can always pick an integral curve. Sorry, my picture is bad. Right, so you can always pick an integral curve that's tangential to M, and then y tilde on gamma of t is exactly y of gamma of t. No matter what extension you pick, it has to restrict to y on M, right? So that shows that this definition is independent of the extension that you pick. Okay, an especially important special case, which we will talk about a lot, is when this projection P is taken to be the orthogonal projection. So you have an induced inner product on Tm, you take this P to be so that it preserves this this inner product to be sorry the orthogonal to be the orthogonal projection, right? All right, so maybe that's it for this lecture. In the next lecture, I am going to use this refined locality to define covariant derivatives along curves, and then using that we are going to introduce this notion of parallel translation, which is actually a much more geometric way of trying to understand what connections is. Also, I still haven't, I mean, you might be wondering why the word connection, right? Why not just covariant differentiation? Why the word connection? The notion of parallel transport will actually explain the etymology of the word connection. Okay, so so maybe that's it for this lecture. Thanks for the attention, and I'll see you in the next lecture.